Good afternoon. For those of you that don't know me, I'm Guillermo and I'm enrolled in a PhD that tries to solve measurement association and tracking problems derived from maneuvering satellites. As you can see on the bottom right corner, this thesis is part of a collaboration with ESA and GMB. Here you can see a figure that shows the number of objects currently being tracked by the US Space Force. So here you can see three discontinuities. The first one corresponds to a Chinese anti-satellite test. Then the second one is an in-orbit collision between Cosmos and Iridium in 2009. And the third one is a recent Russian anti-satellite test that occurred in November 2021. Also, you can see the fast growth recently in the number of active spacecraft, which is mainly due to new mega constellations, the democratization of space access in general. So obviously there is a need to keep track of all of these objects in order to prevent future collisions. So there is a global network of electronic sensors that continuously monitor the Earth's orbital population. So these sensors obtain tracks of objects that need to be processed in order to maintain a catalog of the orbital population. So for each new detected track, we try to correlate it with an existing object. So in which case, we just update the orbit of that object in order to reduce its uncertainty, mainly. If we're not able to do so, then we try to detect maneuvers. In which case, if we're successful, we just update the orbit again, considering maneuver has taken place. Otherwise, we try to correlate it against other tracks that has not been yet correlated in order to determine a sufficiently reliable orbit that can be effectively considered an object, right? Then, we just run certain checks to ensure that this object is not a duplicate of an existing one, and also we try to detect whether this is a maneuver state of an already cataloged object. Solve is essentially the sequential state estimation of a maneuvering target, and for this we use the stochastic hybrid systems formulation. Here X represents the state of our target, and M is the mode between two subsequent observations, denoted as, and these observations or measurements are denoted as C. So basically we initially have the probability distribution function for the state at the initial epoch, right? And then we want to propagate it to a subsequent measurement epoch. And basically under the assumption of maneuver or not, right? And then based on the information contained within the measurement, we need to infer whether a maneuver has taken place. And then we update the probability distribution function of the state considering the measurement. The algorithmic approach we've used to solve this particular problem relies on the use of a sequential Monte Carlo filter. So the probability distribution function of a state is given in sample form. Then the samples are propagated using a multi-fidelity propagation method to reduce the computational cost associated to propagate it in the dynamics. Then we also have a post-maneuver state estimator, right, which is the main core of this work, which is based on the measurement space, right? Then we will do a measurement update based on a regularized particle filter, but still we need to maintain multiple hypotheses because the space accessible to maneuvering objects is quite big, so we may do misassociations. Now we will comment on the post-maneuver state estimator. Let me introduce you control distance metric that we've developed for this particular purpose. So suppose you have an initial orbit, right, and then you apply a maneuver at a certain true longitude and another maneuver at a later true longitude. So effectively, two maneuvers are the minimum number required to transfer between two arbitrary orbits, right? So now let us assume that we take the orbits at the final epochs and we assume that the dynamics are Keplerian, right? Then it is possible still to apply two different burns at two different true longitudes. that are compliant with the orbital transfer, right? Essentially, what we propose is to take Gauss planetary equations, assume impulsive maneuvers, and then perform a linear approximation of these Gauss planetary equations, and solve for the couple of burns that, the couple of true longitudes that minimize the number of required burns to be compliant with certain orbital transfer. In parallel, we have developed an alternative control metric tailored to electron propulsion. Hudson and Skiers proposed to approximate any control profile as a Fourier series, and then model the dynamics of the object according to this input. Since the orbit is effectively perturbed by this control input, then it is convenient to average the orbit within one orbital period to obtain some sort of secular dynamics, right? Then we can do a first order approximation for this average dynamics, and we are left with just 14 coefficients to determine, to fully characterize the control input. Then still we need to add an average term, right, to better approximate the dynamics due to the oscillations that the true dynamics have. But still we are left with a linear dependency on these transfer Fourier coefficients. So we can define a control distance metric as the maximum instantaneous thrust required to transfer between an initial and a final orbit. We have two metrics that are very computationally efficient. What can we do with that? There's an interesting concept that has been applied to orbit determination in astrodynamics and is based on the definition of an admissible space where you can seek for your solution, right? So suppose we can divide our steady space into two subspaces, the observable, which is the measurement space, and the unobservable space, right? So we want to define an admissible control region that is compliant with the measurement space and also is upper bounded by some control effort in the unobservable space. So we need a tractable means to compute to approximate this region, and for this we define a centroid which is compliant with the measurement and is closest to the pre-maneuver orbit in the unobservable space. Then we can apply pattern search methods to provide an outer approximation for this region, like a bounding box. And here you can see how it looks like when applied to radar tracks. So you can see that the true post-maneuver state is enclosed by this approximated admissible region. This coarse approximation is sufficient for us, since we will apply Markov chain Monte Carlo sampling methods within this admissible control region to try to infer the posterior state distribution condition of the measurement and maneuver, right? So effectively, we will use an informative prior, which is a uniform distribution in the admissible control region. Then we will evaluate the measurement likelihood in order to try to infer the target distribution, which is, well, the state distribution conditioned on the measurement and then maneuver. And for this, we will apply different hypotheses, right? So we may assume that the post-maneuver state distribution is inversely proportional to the control effort, or we may add additional heuristics based on previous maneuvers or typical control efforts or typical orbital transfers in order to find a good approximation for the posterior target distribution. In this slide, I've gathered some results obtained by application of the proposed methodology. So on the left, you can see that we've been able to overperform current methods based on least squares and multimodal Kalman filters. Besides, we've been able to propose a consistent definition for the sequential estimation of long maneuver sequences or low thrust long duration maneuvers, which you can see on the right. Other work will consider embedding this type of single target filters into multi-target tracking methods in order to consistently resolve data association in the presence of maneuvers. Also, on the right, you can find a list of achievements and papers in case you're interested. So, well, thank you for your attention, and I'll be pleased to answer any question you may have.